we're going to look at some interesting examples that are applications of the formula that we got for converging geometric series in the previous video. So let's recall that S without a subscript represents the infinite sum. So this is the infinite sum is equal to the limit as n goes to infinity of our partial sum. And remember that when we did that, let's just recall, I'm just going to put this on here. This is the limit as n goes to infinity of a sub 1 times 1 minus r to the n over 1 minus r. And remember we talked about that when n was really going to infinity and r is less than 1, so this is if the absolute value of r is less than 1, then this r to the n just becomes 0. 1 minus r would just be 1. So this simplifies to a sub 1 over 1 minus r. So this is what we're going to be using for converging geometric series. So let's take a look at a couple of examples that involve repeating decimals. It turns out that repeating decimals are actually converging geometric series. So let's think about it. If I took 0.3 and added 0.03 and then added 0.003 and then added 0.0003 and I added all those, I would get 0.3333. So that I could think of 0.3 repeating as 0.3 plus 0.03 plus 0.003 plus 0.0003 plus, and then keeping going forever with that. So this is an infinite geometric series because you'll notice as we go from one term to the other, all we're doing is multiplying by 0.1. So if you multiply 0.3 times 0.1, you get 0.03. And if you multiply that by times 0.1, you get 0.003. And then times 0.1 again, 0.0003, etc. So we have a situation here where a sub 1 is 0.3 and r is 0.1. And since 0.1, the absolute value of 0.1 is less than 1, we have a converging geometric series. So this converges. So we can say then that S, the sum of all the terms, the infinite sum, is 0.3 divided by 1 minus 0.1, which is 0.3 divided by 0.9. Well, 0.3 divided by 0.9 is the same as 3/9 because you can just multiply both sides by 10 and move the decimal place. So this is 1/3. And hopefully you recognize, oh, 1/3, yeah, that's the same as 0.3 repeating. That's the same number. So that makes perfect sense. Now something that may or may not make as perfect sense to you is this next one. So we can do the same thing with this and say this is 0.9 plus 0.09 plus 0.009 plus 0.0009 plus ... etc. And we have the same situation going on here, but with a different a sub 1. A sub 1 is 0.9, r is still 0.1, so we still have a converging sequence. We can still use the sum formula to find the sum of all of these terms. So we say S is equal to 0.9 divided by 1 minus 0.1. So this is 0.9 over 0.9, and 0.9 over 0.9 is just 1. So what we're saying here is that 0.9 repeating is equal to 1. Now that, some people find that perfectly fine to believe that, and other people say, no, it's not equal to 1, it's just really close to 1. No, 0.9 repeating equals 1. So let me show you a couple things that might convince you that that is really the case. So first of all, on the calculator. So on the calculator, I'm going to do a couple of things here. I'm going to put in 1 divided by 9 and then do a control enter. 0.1 repeating. 2 divided by 9. 3 divided by 9, which we've already, of course, done. 4 divided by 9. 5 divided by 9. Now you'll notice here that this is 0.555556. That's because my calculator is automatically rounding to 6 decimal places, and so it's rounding the 0.55 to 6 at the end, but it's still 0.5 repeating. 6 divided by 9, 7 divided by 9, 8 divided by 9. So what is 9 divided by 9? Well, clearly 9 divided by 9 is 1. And yet it's also 0.9 repeating if you follow this pattern. So 0.9 repeating must actually equal 1. Now you might have said, well, the calculator just rounded it up. Well, you might think of it that way as kind of an infinite rounding up, but really this is one and the same thing. Now let's take a look at one more. Okay, so I'm just going to write 1 9 equals 0.111, 2 9ths equals 0.222, etc., etc. 9 9ths equals 0.999, but it really equals 1. Okay. Now another thing, so actually I'm going to write calculator up here. This is calculator. So there's one other thing that shows you that. Now, here's another way to look at this. Is think about, let's say x equals 0.9 repeating. So 10x would be 10 times that, so that means you'd move the decimal place over 1, so it'd be 9.99 repeating. Okay? So let me take 10x and subtract x. So I'm going to say 10x is 9.999 repeating. X equals 0.999 repeating. Subtract one from the other. On the left-hand side, I will get 9x. On the right-hand side, if I do 9.9 repeating divided by 0.9 repeating, all of the repeating decimals subtract out, and I just get 9x equals 9. So x is 9 over 9, which is 1. And yet, x is also 0.9 repeating because I defined it to be that way at the beginning. So there's another proof that 0.9 repeating is actually 1. So you can use a converging geometric series to actually evaluate fractions, repeating decimals, and turn them into fractions. Now this is not really a converging sequence per se. It actually has a couple of this little thing that I'm going to do now has a couple of geometric sequences, and it's just an interesting pattern that I wanted to show you. This figure is known as a fractal. When you take a shape and you divide it into smaller repeatedly smaller and smaller copies of itself, then this is called a fractal. So let's say, for the sake of argument, that the area of the black square in figure 1 equals 81 square units. So that means its two sides have side lengths of 9. That would mean that if we divide this side into 3 equal parts, this figure has 5 squares that have areas of 3 each. I'm sorry, the areas are 9, but the side lengths are 3. If we divide each of these squares into the side lengths into thirds and form 5 smaller squares, each of these little squares have a side length of 1. Okay, so that's the pattern we're doing, first of all. So I want to make a little chart here and just looking at these figures. So the first column is just the figure number. Okay, so we have figure number 1, 2, and 3. The second thing I want to put in is the side length. So the side length for figure 1 is 9. The side length for figure 2 is 3. The side length for figure number 3 is 1. The next thing I want to put in is the number of squares in the figure. So the first figure, figure 1, has 1 square. Figure 2 has 5 squares. Figure 3 has 5 times 5. Each of the 5 squares are divided into 5 smaller squares, so this is 25 squares. Now let's look at what happens when we find the area and the perimeter of the black region. So let's find the area and the perimeter of the black region. So the area of the first one clearly is 9 times 9 is 81. And I'm actually going to write this as 9 squared. 9 squared equals 81. And we have 1 square, so it's 1 times 9 squared. The second one, I have 5 squares, and each of them has an area of 3 squared. So 5 times 3 squared, which is 5 times 9, which is 45. In the third figure, I now have 25 squares, but they're each only a 1 by 1 square, so it's 25 times 1 squared, which is 25. Okay, so those are the areas that I have so far. Now let's look at the perimeters. So the perimeter, of course, is the total area around the edges of the square. So the first one, if the squares are 9 units long on each edge, then my perimeter would just be 4 times 9, which is 36. In the second one, the perimeter is 4 times 3 for 1 square, but I have 5 squares. So it's 5 times 4 times 3. 20 times 3 is 60, so the perimeter is 60 units long. In the third one, my perimeter is 4 times 1, so the perimeter of 1 square is 4, but I have 25 squares, so it's 25 times 4 times 1, which is 100. Now, isn't this odd? The areas are getting smaller, but the perimeters are getting bigger. So let's see what happens if we went to the fourth square. So what I want you to notice is this pattern. Look what's happening with the side links. 9, 3, 1. I am multiplying by 1/3 or dividing by 3 each time. 9 divided by 3 is 3, divided by 3 is 1. So the next one, if I divided everything to be 1/3 of what it was before, the side length for the next figure would actually be 1/3. And then if you look at the pattern of how many squares there are, 1 square is divided into 5. Each of those 5 is divided into another 5. So now I have 25. Each of those 25 would be divided into another 5 squares. So now I would have 5 times 25, which would be 125. So what I have here are two geometric patterns. This is a geometric pattern that is converging. It's getting the side length, the terms are getting smaller because I'm multiplying by 1/3 each time. So times 1/3 times 1/3 times 1/3. This is a geometric pattern that's diverging because I'm multiplying by 5 each time. Notice that both patterns affect the area and both patterns affect the perimeter, because here the number of squares is increasing, but the area of the squares is decreasing. So this next one would be 125 times 1/3 squared. 125 divided by 1/3 would be 125 over 9, which ends up being 13.888. And here we have 125 squares times the perimeter, which is 4 times 1/3. So I would have 125 times 4, which is 500 divided by 3, which turns out to be 166.66. So notice what we have here is the area is decreasing and the perimeter is increasing, and in fact these may even form some sort of a pattern as far as a series, because each time the area is each time here this has 9 squared, 3 squared, 1 squared, 1/3 squared, 1, 5, 25, 125. It's possible that this would even make a pattern that was very, a consistent pattern, because I'm going to be multiplying this by 5, dividing this by 3. So basically this was 81. This would be 9. This would be 1. This would be 1/9. So this is 1/9 times 1/9 times 1/9, and this is 5 times 5 times 5. So basically, I am multiplying each number times 5/9 here. So this is times 5/9, times 5/9, times 5/9, etc. This one is being divided by 3 each time, 9, 3, 1, 1/3, and being multiplied, if we start out this being 1 times 5 times 3 times 125. So this is actually going up times 5/3 each time. Times 5/3 times 5/3. So this is a diverging geometric sequence. So we could actually find the sum of the area, and we could actually, but the perimeter is going to infinity. So we can say here, if we keep multiplying by 5/9 each time, this number is going to get smaller and smaller and smaller and smaller. The terms, the area, the terms are going to get close to 0, while the perimeter is going to infinity. So for the area, they are, as n goes to infinity, I should put here, as n goes to infinity, as n goes to infinity, the area is going to get to 0. Because as we keep multiplying by 5/9 over and over and over, these numbers are going to get smaller and smaller and smaller and smaller and smaller and smaller, and basically end up being close to 0, infinitely close to 0. But the perimeter, on the other hand, is getting bigger and bigger and bigger, and it's going to infinity. So this is just kind of an odd characteristic of fractals. Fractals have this characteristic that as one dimension gets infinitely small, the other dimension gets infinitely big, which doesn't happen with regular shapes. Like if I just make a square smaller, its perimeter gets smaller and its area gets smaller. If I make a square bigger, its perimeter gets bigger and its area gets bigger. But fractals, on the other hand, have very weird dimensions. And that's actually called a fraction. That's why they're called fractals. They're fractured dimensions. So just thought I'd introduce that. It's kind of a fun little topic. There's lots and lots of stuff on the internet about fractals if you're interested.